You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have a returning guest, Ethan Siegel. He's an American theoretical astrophysicist and a science writer, and he's been studying Big Bang Theory, what comes before it, what comes after it, and what happened during the Big Bang. In the past, he's been a professor at Lewis and Clark College, and he's a prolific blogger. He has a blog called Starts with a Bang. You can find it on Forbes.com, on science blogs, and it appears to be syndicated on Medium and a lot of other places. I've spoken to Ethan on the podcast. This will be the third time, and I actually speak to him pretty frequently, every few months or so, to learn physics. It's just something I've always wanted to do, and Ethan's very gracious about talking to me for a short period of time on the phone and answering questions. He's a great guy, and I'm really glad to have him back on the podcast. We're going to talk about his upcoming book that talks about what came before the Big Bang. I didn't know anything came before the Big Bang. I thought that was the start of our universe and of time and space itself, but it appears that that's not the case. So it's going to be a very interesting interview. So listen in, and I think you're going to get a lot out of it.
All right, Ethan. Well, thanks for coming on the podcast. I really appreciate you being here.
Oh, it's always my pleasure to be on the Future Tech Podcast. There are so many interesting things going on and happening in science and technology and here on planet Earth and beyond that I wouldn't miss the chance to talk about them and share them with you and your listeners.
Yeah, thank you. So today we're going to talk about something that I thought was true and I thought was universally believed. It probably is, but I thought, the universe and everything in it started from the Big Bang, and the Big Bang was like the singularity, this infinitely dense, infinitely small point that from which everything exploded outwards and made our universe. But you're coming out with a new book. It sounds like, end of the year, that's going to be shed light on a different mechanism. So, I hope I haven't garbled that, but tell me what the book's about.
No, and you're absolutely right. If you've been paying attention to what physicists talk about, what lay people talk about, the universe began with the Big Bang, and it began some, 13.8 billion years ago, where all the matter and all the energy in the universe was compressed into this single dense point, which, started exploding or expanding or however you want to view it, and that gave rise to the entire observable universe. And that's been the story for a really long time. But if you were to talk to a theoretical physicist who studies what I study, which is called cosmology, that's the science of the entire universe itself, then you would know in this branch of theoretical astrophysics that the Big Bang hasn't been treated as the beginning or the birth of space and time or a singularity in pretty much 40 years. And so that's what this book that I've written is all about. That's what it's, that's the key point that I'd like to communicate to people is that, hey, you might think that going before the Big Bang or saying the Big Bang didn't happen is completely against science and not scientific, but we do the things we do, and we conclude the things we conclude not because we favor them or because they sound good to us, but because we have ways of testing the universe and finding out, hey, what are you really like? We ask it questions about itself, and if we ask these questions in clever ways, it will tell us the answers written in the measurements and observations we can make of the universe itself. So that's what my whole book is about, is telling you, okay, yes, we have this story of the Big Bang, and we can go through the details of it, but there are big questions about the universe that the Big Bang is completely incapable of answering. And this is just like it is in any other field, in anything you look at. Let's say you were looking at life on Earth and you wanted to know, where did I come from? Well, you would look at your biological parents and their DNA mixed together, and that would be where you came from, and you could trace them back to their parents, and so on and so on. And eventually you might come to some organism that didn't evolve that way. And maybe it didn't evolve that way because gender hadn't evolved yet, and there was no way for two separate parents to have an offspring because things didn't divide that way, things didn't reproduce that way. And you could go back even earlier and say, well, what about this very first life form that existed, the thing that was right on the border between life and non-life? Well, you can't use Darwin's theory of evolution to talk about how life arose from non-life, because that goes beyond the scope of Darwin's theory. At the same time, you could go even deeper than Darwin's theory and say, hey, how does inheritance work? How did I get my genetic traits that I have from my biological parents? And the answer is, well, Darwin won't tell you that. You have to go beyond Darwin into the science of genetics. And then beyond genetics, you can look at, well, what is it that encodes all of this genetic information? And you have the science of DNA. So just like it is in biology, where you have theories that have a range of validity, and then you either go deeper or you go outside of that scope, so it is in astrophysics, where the Big Bang can give you a whole slew of interesting information, but it itself has some fundamental limitations to it.
So let's talk about it that way. So I guess first thing that occurs to me is now when people say, oh yeah, well, what came before the Big Bang? You've got an answer, which is nice. And you can
I do have an answer. I do have an answer. And spoiler alert, it's a different theory called cosmological inflation. But when you talk about before the Big Bang, what I want to do is I want to make you think about what it is that we would even need something before the Big Bang, right? We don't just come up with theories because they're fun to come up with. I mean, some people do, but as scientists, that's not why we're compelled to do it. We're not just messing around in the sandbox trying to say, like, oh, what can we build? What can we look at? What can we construct? What we want to do, we always have these motivations where we're trying to solve some sort of problem, where we're trying to look for a solution to some sort of puzzle. And the big puzzle we have in the universe is we always want to know, why does it have the properties that we observe it to have? Part of the reason the Big Bang is so successful is because we saw something that we couldn't really explain. Almost 100 years ago now, we started looking at distant galaxies, and we saw that they're
one second, Ethan. So just to put a quick frame around it, so that's what I wanted to ask you is what did the Big Bang answer for us, and what did it explain, and then what didn't it explain, and then let's move to cosmic inflation. So sounds like
that all sounds great. So what the Big Bang did explain, right? Back in the 1920s, we discovered the universe was expanding. That was weird for a lot of people, but that was also a new prediction of Einstein's general relativity. It said, Einstein's theory says if you have a universe that's full of matter everywhere you look in equal amounts, roughly equal amounts, then it can't be stable. It won't be static. Either that universe needs to expand or contract. And Einstein didn't like that. Einstein, when he discovered that about his theory, said, nah, the universe has to be static. It has to be stable. So I'm going to put in an extra term to force it to be stable. So he put in an extra term. It didn't make the universe stable. It just made it clear to everyone else that this is not right. Well, in the 1920s, people were observing these distant galaxies, what we now know are galaxies, and they found that the further away you look, the farther away you find a galaxy, the more its light appears to be redshifted. So if you have atoms anywhere in the universe, they have the same quantum rules that govern them. They have the same energy levels that transition from one to another, and they have the same wavelengths of light that they absorb and emit when they do these atomic transitions. So you say, okay, I'm going to look at the signatures of hydrogen here in our own galaxy. And then I'm going to look in these distant galaxies. And what you find is the farther away a galaxy is, the more that hydrogen light is shifted towards redder and redder wavelengths. The reason this works in an expanding universe is because the light, when it gets emitted or absorbed, it has a specific wavelength, but then it has to travel to you through this expanding universe, which means that light gets stretched. If I held my hands a fixed distance apart and said, this is the wavelength of my light, and I kept my hands at that distance, nothing would change about it. But if I said space is expanding, that would compel my hands to stretch apart, which would stretch that wavelength of light, which would make it redder. So what the Big Bang said is, hey, let's extrapolate for a minute. If space is expanding and growing bigger today, that means objects are getting farther apart, the universe is getting less dense, and light is redshifting, which means it's getting stretched towards colder temperatures and longer wavelengths. So if that's what the future looks like, then what did the past look like? Well, it would be the opposite. If things are expanding today, that means the universe was smaller in the past. It means it was denser in the past. And if wavelengths were shorter, that means it was hotter in the past. So you take all of those things, smaller, hotter, denser, and you keep extrapolating backwards and backwards and backwards. What winds up happening? This is the big idea of the Big Bang. It says that you would reach a point where gravitation hasn't had enough time to work to form stars and galaxies, because that's how it works over time. Even in an expanding universe, gravitation is something that builds and builds and builds. As you get more and more mass collected into a single location, it gets better at attracting more and more mass. So as we look to greater distances, we should find galaxies that are smaller, less evolved, and greater in number until you reach a point where there aren't any galaxies. And we've looked and we've seen it. We can go back further and say, you know what? When you go even hotter and even denser, maybe that wavelength of light can get so short that light is so energetic that we can't even form neutral atoms, that we would just ionize them, that we would just kick the electrons off of the nuclei that they were bound to. And we look back and we actually find the leftover glow from that transition. That's what we call the cosmic microwave background, because this was light that was energetic enough to ionize atoms 13.8 billion years ago. But as the universe has expanded, it's gotten redder and redder and more shifted. So it goes from visible light to infrared all the way into the microwave part of the spectrum. And that's why we call it the cosmic microwave background. So that's how we confirm the Big Bang. That's how we prove to ourselves that the Big Bang was a good description of the universe. And we can go back further to before we could form atomic nuclei. And guess what? We see the predicted abundance of the light elements of hydrogen and deuterium and helium 3 and helium-4 and lithium. We've observed that it's consistent with the Big Bang's predictions. So it's very tempting to go back arbitrarily far and say, well, what if we go to the ultimate limit of hot and dense? Well, we'd achieve infinite temperatures, we'd achieve infinite densities, and we'd extrapolate the universe back all the way, like you said earlier, into a singularity, where all of space and all of time is contained within a single point in the universe. That's the original idea of the Big Bang, and that's probably where most people's ideas about it stop.
Yeah, okay, yeah, definitely. And so where does that break down?
Well, it
what
breaks
happens
down because one of the things you have to ask yourself whenever you make a theory like that, whenever you have this big framework set up and you want to ask, hey, okay, this is my picture for what the young universe was like, and here's what the universe is like as you step forward in time, and here's what you should see as a result. Well, one of the things we like to do is we like to say, well, what have we seen about the universe, and how does that compare to what we expected to see? Well, if you went and looked to your left, and you looked to the edge of the universe 46 billion light years away, right? The expanding universe, this is the limit of what we can see. If you look to the left, you're going to see the universe with a particular temperature and a particular density and a particular set of properties. And you say, okay, that's what the universe looks like on my left. What does the universe look like on my right? What does the universe look like in the complete opposite direction? What you discover is that the universe looks, on the large scale average, precisely the same. It's got the same temperature to 1 part in about 30,000. It's got the same density to 1 part in about 30,000. But that doesn't make sense if you ask the Big Bang, what do you predict? Because if you were to predict, from the Big Bang, what should I get? Well, you should have temperature fluctuations that are on the order of the actual temperature. So right now, if I look in any direction, I measure the temperature of the cosmic microwave background, and I get something like about 3 Kelvin, 3 degrees above absolute zero. Well, if I then go ahead and say, okay, well, what is the temperature on the left and what is the temperature on the right, I would expect that they might be different from one another by 1 or 2 or 3 or 5 Kelvin, that they might fluctuate by that amount, but they don't.
But why is that? Because you picture that the Big Bang expanded radially outwards from just a certain point, so you'd see differences depending on where you look?
Well, what you expect would happen, remember, if the Big Bang is the birth of space and time, then it happens everywhere at once. And what that means is, sure, you're going to have differences in how things evolve. Because in some region, I might have slightly more matter than others, and that region is probably going to grow into stars and galaxies and structure. We know that the universe couldn't have been born perfectly uniform, because if it were born exactly the same everywhere, there would be no way for one region to preferentially attract more matter than the other. The fact that we live in a universe today that's full of stars and galaxies and clusters of galaxies making up this great cosmic web tells us that the universe couldn't have been born perfectly uniform. So if it isn't born perfectly uniform, then you can say, okay, well, according to the Big Bang, what should these imperfections have been like? And the answer is they should be the same scale as the temperature themselves, as the temperature itself, as the average density itself. So that's one big puzzle, is why do we see the universe with the same properties everywhere if there was nothing that compelled it to have the exact same properties everywhere? Why are these fluctuations that gave rise to stars and galaxies and everything we see, why do they exist, but simultaneously, why are they so small? This is what we call a fine-tuning problem in the universe, where it's sort of like if you flipped a coin and the coin doesn't land heads and doesn't land tails, but lands on its side, you'd say that's a pretty unusual event. If you flipped that coin 10 times and it landed on its side 10 times, you would say, okay, now this is really weird. Well, everywhere we look in the universe, we would expect, if it were going to have the same temperature properties everywhere, we would expect that it would be sort of like it is in your room, right? You have a room, you close all the doors and windows, and you set off a heater in one corner of the room. What's going to happen? Well, that corner of the room will heat up, but if you give it enough time, all of that hot gas is going to diffuse throughout the rest of the room. It's going to take time for things to come to what we call thermal equilibrium, that the universe, or your room, is going to reach the same temperature everywhere. Well, when you look to the left in the universe and you look to the right in the universe, they haven't had time to do that. They haven't had time to come to thermal equilibrium or reach the same temperature everywhere. Something had to have happened early on in order to give them almost exactly the same properties everywhere, but to have those properties be slightly different so that you could form stars and galaxies, but not form hugely different amounts of stars and galaxies. This is a strange thing that the Big Bang can't explain. And there are others.
Right, to recap, before we move forward, the temperature differences we should expect if there was a Big Bang from singularity would be 1 to 5 Kelvin degree difference, but it's what, orders of magnitude less than that? You said it's 1 part in 30,000?
Yeah, that's right. You would expect that temperature fluctuations or density fluctuations would generally be on the same order of magnitude as your density or your temperature. But we don't have that. We have things that are tens of thousands of times less than that. That's the scale of our fluctuations. If we just said, oh, yeah, that's the way the Big Bang must have been, that doesn't teach us anything. That doesn't give us an answer. That just is a puzzle without a solution.
Okay. What other things have we seen?
So we've got other puzzles without a solution. If I were to go back to the moment of the Big Bang and say, okay, what do I need in order to get the universe I have today? You'd say, okay, I need basically there's a race going on. We have the initial expansion of the universe and the rate that it expands and how quickly it expands. And counteracting that, we have the force of gravity that acts on everything present in the universe. We have all the matter and all the radiation and all the dark matter and all the dark energy and all of these different types of energy, neutrinos, etc., that contribute to the gravitational force. So on one hand, you have this initial expansion of the universe working to drive everything apart. And then you have all the forms of energy in the universe working to pull everything back together. This is like a giant cosmic race. It's a race between the expansion driving everything apart, and it's a race between gravity working to pull everything back together. The Big Bang was the starting gun, and then you say, okay, who's going to win this race? Well, if
quick question here.
Yeah.
If the Big Bang happened everywhere, any place in the universe, let's say right now where there's matter, wouldn't it, by gravitation, want to make essentially a lumpy universe versus a smooth, uniform one, instead of pulling everything back together to a given point or origin?
Well, that depends. I mean, that's a very good question. That's a very deep question. That depends on, what the difference is between what we call the local density, which is the density in one point, and the global density, which is the average density throughout the whole universe. So you're absolutely right when you think on local scales. You say, okay, here we are in a galaxy, in a group of galaxies. We're a clump of matter. We're trying to pull more and more matter in to where we are. And we've been somewhat successful at that. The Milky Way, Andromeda, and maybe 60 or 70 dwarf galaxies, we've all clumped and clustered together. We all were drawn into the same, gravitationally overdense region of the universe. And that's how it works on small scales. But it also works on a large global scale. If the overall average density of the universe is too big for an initial expansion rate, what's going to happen? You're actually going to get a universe that will expand for a time, but gravitation will keep pulling everything back together. This universe will expand and slow down and eventually reach some maximum size, and it will stop expanding and turn around in reverse and start contracting. And that universe will end in a big crunch. That's a possible fate of our universe. And that's if you look at the universe not on a small local scale, but on a global average scale.
Okay.
All right.
Throwing a ball up in the air, it goes up slower and slower and slower, peaks, and starts coming down faster and faster. So
it is like that, except it's looking at any 2 points in the universe that start moving away from each other, reach a maximum size, and start moving back towards each other. In a universe with the Big Bang, if gravitation wins that race between expansion and gravity, then it will recollapse and our universe will end in a big crunch. Well, you can also say, well, what if it ended the other way? What if the expansion rate was the winner and gravitation was the loser, well, then expansion would be a runaway thing. Things would expand, and the expansion rate would slow down as gravity tried to pull everything back together, but it would fail. And so, what you get in a universe like that is the expansion rate will drop and drop, but it will never reach zero. Things will keep expanding away indefinitely far into the future, and you will wind up with a fate that we call the big freeze or the big chill, depending on who you ask. And this is a universe where, yeah, you'll get these little clumps of matter, but they'll all be unbound to each other, and they'll all keep expanding away from each other indefinitely into the future. Well,
Gotcha.
every once in a while, you tell a story, and it makes me think of Goldilocks and the Three Bears, where, okay, we know what happens if the porridge is too hot, and we know what happens if the porridge is too cold, but what happens if the porridge is just right? What happens if the universe's initial expansion rate from the moment of the Big Bang and the universe's gravitation from all the different sources of energy within it, what if they balance each other exactly? That would create a universe that was like balanced right on a knife's edge, where it somehow managed to just be right on the border, where if you had one more proton in the universe, it would recollapse, but you don't have it, and so the expansion rate instead asymptotes to zero, but never turns around. That was the universe we thought we lived in for a very long time. It looked for the best of our observations that this is exactly what we have. And the reason it looked that way is because when we measure the curvature of the universe, we find that it's spatially flat. This is not something that will generally happen. It's something that, again, we say it had to have been very finely tuned. For some reason, the universe was born with this perfect balance between the expansion rate and the amount of stuff in it. This is a big puzzle. And there's another big puzzle, too. If you say, oh, the universe was arbitrarily hot and arbitrarily dense, then it should be possible to produce every particle, every theoretical particle that we can imagine that's consistent with our physical theories. One such type of particle that ought to exist is called magnetic monopoles. In our universe, we have what we call electric monopoles, which is to say things could have positive or negative electric charges, and when those electric charges move through space, they create electric currents which make magnetic fields. So we have electricity and we have magnetism. Well, in almost every extension we have to the universe as we know it, when we look to those extremely high energies, we expect that there will also be magnetic monopoles, that there will be fundamental that there will be fundamental magnetic charges that we can't get rid of. So what happens there? Well, you should be able to build big experiments if they exist, where you have these big coils of wire, and every time a magnetic monopole passes through them, we'll say, there it is, and we can measure what's actually out there. Well, we've been doing these experiments for decades, and there was only ever one detection of a magnetic monopole, and it failed to be confirmed. That was way back in 1982. So we're pretty sure that was not a real detection, and people are not working on that anymore because of all the failed experiments that have come before then and since then and overlapped with that one as well. So we have these big puzzles. Why is the universe the same temperature in all directions to 1 part in 30,000? Why is the universe perfectly spatially flat and balanced between the expansion rate and all the energy in the universe exactly as far as we can tell? And why are there no high-energy relics left over from this early hot, dense state if the temperatures got arbitrarily high? These are some of the puzzles with the Big Bang that the Big Bang itself cannot explain.
Quick question there. You said the expansion rate appears to be balanced with the amount of matter in the universe. So does that mean that our acceleration has slowed to the point where we've reached the inflection point where it's going to start going the other way, or what does that explain?
So we now know we live in a universe filled with dark energy, where there's this energy inherent to the fabric of space itself, and that wasn't something that we knew when we first started questioning the Big Bang. Um, but what this tells us is that yes, the universe is expanding. The universe started out balanced between the expansion rate and the amount of energy within it. And it started out balanced to like at least like 20 or 30 significant digits, where if you're writing out, okay, what's the density of the universe, and you write out your number, you have to go into like beyond the 30th digit to find that mismatch between the expansion rate and the amount of stuff in it. The fact that our expansion is accelerating today just tells us actually one of these forms of energy is not matter or dark matter or radiation or neutrinos. It's this additional form of energy inherent to space itself. So we're going to keep expanding into the future, but the geometry of the universe is still going to remain flat. And this is something we've actually been able to measure by looking at the patterns of fluctuations in that leftover glow from the Big Bang in the cosmic microwave background. We've been able to constrain that our universe is so spatially flat, so indistinguishable from flat, that if it had any curvature at all, like it was a tiny, tiny part of a big sphere that you can't see the curvature because you're only seeing a little section of the sphere, sort of like how your backyard doesn't show you that Earth is curved. We know our universe is so flat that the tiny part of it that we can observe, if the universe, the larger universe that we're a part of, isn't flat, it has to be hundreds of times the radius of what we've already seen.
Okay.
So these are some puzzles.
We got all these issues. All right.
Yeah, and you've really got a couple of options from a scientific point of view if that's your situation. The first option is to say, well, that must have been the way the universe was born. Okay, let's go home. Let's pack our bags and let's go home. We did everything we could do. There are some puzzles and we can't solve them anymore. And that's what I like to call giving up on science. We just throw our hands in the air, say, well, the Big Bang was born. It must have been born with these conditions to give rise to what we see, and that's it. The more satisfying option, the option that keeps, people like me who are theoretical physicists like thinking about this, is saying, okay, if we have the Big Bang, and the Big Bang makes these successful predictions, and also it has these puzzles that it can't explain, then what can we do to go beyond that? We should try to come up with a new theory that, number one, reproduces all of the successes of the Big Bang. Number two, it's got to explain these puzzles that the Big Bang is agnostic about. The Big Bang doesn't explain these puzzles, but a new theory had better. A new theory had better say, okay, I'm going to come along, I'm going to explain the Big Bang, and I'm also going to explain these puzzles that the Big Bang can explain. And then we'll go even further and demand, actually, it's not enough to just do that. We also need you to go out and make new predictions about something we should observe in our universe that we can go out, measure, and tell whether your theory gives correct predictions or not. This might sound like a really tall order, but this is what we've demanded of all our physical theories when they wanted to replace the old one. You might have read stories about Einstein's general relativity and what a revolution it was to go from Newtonian gravity to Einstein's theory of general relativity. Well, Einstein had to do all of that. He had to produce a theory that when you took what we call the weak field limit, which is to say when you're far away from masses rather than being super close to them, you should get Newton's laws back. You should get orbital dynamics and planetary motion and how objects fall on Earth. You should get all of that back. But you also need to explain these weird things that Newton's theory couldn't explain, like why does Mercury violate Kepler's laws when we look at its planetary motion? And the answer is actually because space-time is curved very close to the limb of the sun, and Mercury, being the innermost planet, has that extra experience of space-time curvature. That was the puzzle that Newtonian gravity couldn't explain that Einstein and others were looking at. We also needed Einstein to say, you know what, I'm going to make some new predictions. I also predict that light should be bent by large masses, and that there should be gravitational redshift and gravitational time dilation and all these other subtle effects. This is why, even though general relativity was proposed in 1915 and people had worked out solutions to it, like the solution for a black hole was worked out in 1916, and the solution for an expanding universe was worked out in 1917. I think Willem de Sitter was the first to work out an expanding universe solution. No one really was converted into saying relativity must be right, must be our theory of gravity until 1919, because that was when we made the observations of where are stars located near the sun during a total solar eclipse. And we found, because you can view stars when the sun is blocked out by the moon during an eclipse, we were able to measure stars close to where the sun was located at the time and found that the light from them was in fact bent, consistent with Einstein's predictions and different from Newton's predictions. And that was how we confirmed Einstein's relativity. So if we want to do that same thing for a theory that replaces the Big Bang, we need for it to make all of the Big Bang successes reproducible. We need it to explain these puzzles that the Big Bang has no explanation for, and we need it to go out and make new predictions that have never been tested that we can go out and look for and say, how does this stack up?
Makes sense. Okay.
Tall order, right?
Well, like you said, that's the whole goal of science, is never to give up and throw in the towel. But all right, how can we, what kind of experiments can we do, thought or otherwise, to figure stuff out for real? So what have they figured out for reals?
That's right. So this really got started in late 1979. There was a scientist named Alan Guth who was thinking about these problems, with the Big Bang. And he realized, he even wrote down in his notes, which still exist, spectacular realization, and put stars in a box around it. And what he said was this. He said, if inflation happened, which is basically if the universe underwent a period prior to being described by the Big Bang, being hot and dense and full of matter and energy, if instead the universe were filled with a form of energy that was inherent to the fabric of space itself, what would happen? And he called this inflation. And he said, well, what would happen was your little part of the universe that has this energy inherent to space, it would start expanding at an exponential rate. And I want to give you an idea in your head of how big an exponential is, right? If I gave you a sequence that went 2, 4, 6, 8, 10, you would say, oh, I know how to get from one term to the next. I just add 2. And that would get you 2, 4, 6, 8, 10, and all the next terms would be 12, 14, 16, and so on. That's one way that numbers can increase or grow. You can say, well, I want it to grow faster than that. And what if we go 2, 4, 8, 16, 32? You'll say, oh, I know what I'm doing. I'm taking that last term and I'm multiplying by 2. That's what's known as a geometric series instead of an arithmetic series. Instead of adding, we're multiplying, and that makes things grow faster. Well, there's another possibility for how things can grow, and I want you to think about this sequence. 2, 4, 16, 256, 65,336, 536. What I'm doing now is I'm taking the previous term and I'm squaring it. This goes up even faster than a geometric series. If I go 2 squared is 4, and 4 squared is 16, and 16 squared is 256, and I keep going like that, what I'm doing is I'm saying, wow, as I go forward and forward and forward, things are growing based on how large they were previously, and they will double in size in every dimension. If we live in a three-dimensional universe, and I started with a universe of a specific size, and I say, okay, it's expanding exponentially, that means a little bit of time later, if my universe were a size of 1, if I double the length and double the width and double the depth, now it's a size of 8. If I come back a little time later and say it's doubled again, well, now it's going to be double the length and double the width and double the depth. It's going to be 64 times as big as it was. It's going to be, because it's going to be wherever it was twice as big before. Now it's going to be 4 times the length and 4 times the width and 4 times the depth. So that's actually going to be 4 cubed. So it keeps going up and up and up exponentially. Things get large really, really fast. And his realization for this was basically saying the following: if my universe expands exponentially, if it inflates like this, then in very short order, what I consider my observable universe, what I consider, all the things I can see since the Big Bang, it was all contained within this one patch that was inflating in the past. So why is it the same temperature everywhere? Because at some point in the distant past, that region of space, it had enough time to talk to each other, to exchange information, to come to equilibrium. And then inflation happened, and now all of those uniform properties are stretched across the universe. So when I look to the left and I look to the right, the reason they're the same temperature everywhere is because they were once in contact at some point in the distant past, either in the early stages of inflation or before inflation happened. You can look at the flatness problem and say, hey, why does the expansion rate and the amount of stuff in the universe balance so well? Why doesn't space have any observable curvature to it? And the answer is, well, if inflation happened, then what that means is all of this energy that was inherent to space itself, that determines the expansion rate. When inflation came to an end, all of that energy got converted into matter and radiation and dark matter and all those other forms of energy. The reason that they're so perfectly balanced is because inflation has a way of balancing them. It also explains that the universe looks flat because if something gets stretched to be enormous, to be so much bigger than what we can observe, it's going to look flat to us because the part we can see is indistinguishable from flat. The same way your backyard doesn't have the signs of Earth's curvature on it because the little part of your backyard you can access is too small to measure the overall curvature of Earth. And finally, that last problem of where are all those high energy relics from an arbitrarily hot state? Well, if the universe inflated and then inflation came to an end, we don't get infinite temperatures. We don't get infinite densities. We only reach a maximum temperature that's set by the energy scale of inflation. So if inflation can give us a universe that looks like a universe that started with the Big Bang, that gives you that hot, dense, expanding early state that's full of matter and radiation, and also solves the problem of why is it the same temperature everywhere? Why is it flat and of, a perfectly balanced expansion rate and energy density? And why doesn't it have these leftover high energy relics? That's a huge, huge step forward. That's why inflation is so compelling for everyone who's interested in the origin of our universe.
All right, so a couple questions here. If you take a an arbitrary, or an imaginary cube of space,
Mm-hmm.
the vacuum out there, is the reason that, you say like space has a fabric. I don't know what the fabric's composed of, but if it didn't have a fabric, would an arbitrary part of the vacuum of space have zero temperature, 0 Kelvin, instead of 3 Kelvin, for instance?
Well,
Is it the fact that it has temperature that means that it contains energy in some form to give it a temperature?
Well, we have to be careful about that. The temperature we have for the universe, that 3 Kelvin I told you about, that's not a temperature from empty space itself. That's a temperature from all of the photons from the Big Bang, from all of these particles of light that fill the universe. If you were to take a cubic centimeter of space and say, hey, what's in this? You would actually find a little more than 400 photons left over from the Big Bang today in that cubic centimeter. That's where that temperature of 3 Kelvin comes from. That's where that temperature comes from. But beyond that, there's an energy. If you were to take all those photons away, there's this energy that comes along with the fabric of space itself. Today we call that dark energy, and it's a very small value. But back during inflation, we hypothesized that that must have been a very large value. And that's why we could have had a Big Bang that was hot. When that energy got converted into matter and radiation and antimatter and whatever else you can convert it into, it's going to give you an energy density that's equal to whatever the energy density of empty space was, except instead of being inherent to space itself, which causes inflation, it's going to be in the form of particles, which allows the universe to expand like it did in the aftermath of the hot Big Bang. So what we learn from this, if we picture this, is that if we extrapolate backwards, the universe was expanding and cooling, and it was hotter and it was denser, but there's some limit to that. We can't go all the way back to a singularity. There's some limit to how hot and dense it was, and that corresponds to what you achieved when inflation ended and gave rise to all of the particles in our universe today. That's what happened, is we had energy inherent to space, and it got converted into matter, antimatter, and radiation, which is what we call the hot Big Bang, but not a singularity.
So you're saying inflation proceeded exponentially and then ended, and at the point it ended, that's when matter and radiation and everything started coming out of the fabric of space, and that was the start of the Big Bang, and it proceeded from there. Is that what you're saying?
That's correct. You've got it. And by nature of inflation, because of how rapid and how relentless this exponential expansion is, we can only see the imprint of this final tiny fraction of a second on our universe. We can only see how inflation affected our universe for the final, I think, 10 to the minus 33 seconds of its duration. Anything that happened before that is still beyond the edge of the observable universe.
So that's weird. I mean, then you got to wonder about inflation itself. So you said it has stopped, or do you think I don't know. The universe is still expanding, so I mean, it's ongoing in some sense, but is there an underlying inflation that has stopped, or is that just part of the current expansion?
You are asking super good questions. So these are questions that we think we know the answer to, but we're not sure because we don't have any evidence that we can look to. All we have for that particular question is we look at our theories. We say, okay, I have a universe that's inflating, and what's a good analogy for that? So I can imagine that I've got a big plateau that I'm on, like a big mountain plateau that I'm on, and I've got a ball rolling very slowly across the top of the plateau. And as long as that ball is rolling slowly along the plateau, my universe is inflating. Inflation still goes on. If the ball reaches the edge of the plateau and rolls down off the plateau into into the valley below or off the plateau and, down a cliff or whatever. It's when it gets down to the bottom that signifies the end of inflation and converting all that energy into matter, antimatter, and radiation. Where we are, that happened. That very clearly happened because we live in a universe that's full of stuff. So that very top part of the plateau, we're no longer there. But we think there are other parts outside of our observable universe where inflation didn't end. And the way we can think about that is, remember we talked about that little cube of expanding space where we said, okay, It expanded after a certain amount of time went by. And then all 8 of those cubes expanded and gave us 64. And then those expanded and gave us, and if I do the math in my head, 512. So things keep getting bigger and bigger and bigger. How much of the universe is actually going to end? How much of the universe is going to see inflation end? As it turns out, the universe we know is quantum mechanical, which means that everything is not a particle. You can't picture it as a ball rolling across a plateau. You have to picture it as a quantum field, which is to say that its position is uncertain and the value of the field is uncertain. It spreads out over time. So if your ball rolls slowly enough towards the edge of the plateau, then in different regions of space where you have inflation, I can only give you a probability for where that ball is actually going to be. In many places, it's going to be closer to the edge of the plateau than the average. But in other places, it's going to be closer to the center of the plateau and farther from the edge. So where you have a fluctuation that pushes you back towards the center, inflation is going to continue for longer. We don't know how likely or unlikely it was for us to have inflation end. We only know, based on what we can observe, that inflation did end where we are 13.8 billion years ago. But we have every reason to believe that there are plenty of other places all throughout our universe where, all throughout, I will say, beyond our universe, where maybe inflation didn't end, where it ended for me and I got a hot big bang, and somewhere else it ended for them and they got a hot big bang. But in between, that space was still expanding according to the rules of inflation. So those different universes get pushed apart. This gives us a weird new picture of our universe, and this is also one of the origins of where an idea called the multiverse comes from. It says if you have inflation and you have a quantum mechanical universe, then you will create different pockets of space where inflation ends and you get a hot big bang, but they're going to be separated by expanding space, by exponentially inflationary expanding space. So for us, where we are, inflation ended. But for someone outside of our universe who lived elsewhere in this inflating space-time, they would be able to see that the universe is still inflating.
So if I want to make you at a loss for words, I can ask you how big the multiverse is, or what?
Yeah, and I can give you some big exponential numbers, but really all I can do is I can give you a lower limit, because even with all we know, and I know I want to be mindful of our time here, even though there are tests we can use for those final fractions of a second to say, hey, if inflation happened, what would be its effects on the universe, right? We have observable consequences that inflation should give rise to. We should be able to see a universe where all of these density fluctuations should be on the energy scale of inflation. That should give us an upper limit to how big the fluctuations in, say, the cosmic microwave background should be. They should be much smaller than 1 Kelvin, and they should have a particular spectrum to their fluctuations, which means they should be roughly the same on all scales, but they should be slightly larger magnitude on large scales and slightly smaller magnitude on small scales. And we've seen that. We should say these fluctuations could have been the same temperature everywhere, which means they'd be isothermal, or they could be the same entropy everywhere, which is what we call adiabatic. Inflation predicts they should be 100% adiabatic. And guess what? We've observed them. At least 98.3% of them are adiabatic. So that's another confirmation of inflation. We have others as well that I won't go into all the details of, but those are from the final tiny fraction of a second of inflation, because those are the signatures that persist in our universe today. If you're saying, well, how did inflation get its start? Or did inflation get its start, or was it going on eternally to the past, and then it just happened to end here 13.8 billion years ago? We don't know those answers. There are theorems out there, but there are ways to circumvent those theorems. So even now, even though we've pushed the frontier back further, and we've said, yeah, there doesn't need to be a singularity. You can't extrapolate the Big Bang to arbitrarily hot temperatures and high densities. You can't say the universe, all of space and time, was born if we ran the clock back to this start time of t equals 0, because a period of inflation happened before that. But we can't say how inflation got its start, or how long inflation went on for, or whether inflation lasted eternally or had a beginning, or even whether a singularity and the birth of space and time is an event that happened prior to inflation. We can't say any of those things based on the evidence, because we only have the evidence of our observable universe. And that wipes out any information that existed prior to those final fractions of a second of inflation.
You know, this is the last thing I'll ask you, because I know we're out of time. But what's interesting is the fact that it sounds like it makes it easier for us to study the initial conditions that created the Big Bang, because now it's kind of encapsulated. There was something before it. It didn't start from a singularity, so maybe the math gets easier. Maybe we can calculate the temperature conditions and all the other conditions that started the Big Bang, that caused the inflation to stop and to go into this new regime.
That's a great question, and that's actually what the scientific field of early universe studies focuses on today, is saying, okay, we can go back to the Big Bang, and in the extreme earliest stages, we can look at what was inflation like. We have different models of inflation that make slightly different predictions for some of the parameters in our universe, and the better we observe what those parameters are, the better we make those measurements, the more we can do to constrain, inflation could have been like this, but not like that. It could have been this type of model, but not that type of model. What we're doing right now, when we make these early observations and study the signatures left over from the first few seconds or fractions of a second of the universe, this is what we're doing. We're working to not only understand the earliest times in the Big Bang, but the final times in inflation, and understanding what it was like before the Big Bang happened. This is not in the realm of theology or philosophy. This is science. This is something where our physical theories connect to observable and measurable quantities. And that's how we know that our universe didn't begin with the Big Bang, but it began before the Big Bang with cosmic inflation, and possibly something even working before that to set it up.
Well, very cool, Ethan. This is awesome stuff, and I'm like happy that I'm hanging on to the edge of the fabric of understanding and starting to understand this a bit. So
that's where you should be, right? Why should you not be at the same place that scientists are? Why should you have to digest your popular science that's 40 years out of date? Why can't we have the public understanding of science be caught up to where scientists actually are? That's why the world needs this book, and that's why the world needs to hear this story.
Okay, well, excellent. Well, when will the world hear about the book? What's the ballpark on when do you think it'll be coming out? Scholastic Publishing?
It's all publisher dependent, but my best ballpark estimate is for the first few months, the first quarter of 2020. But you never know. I'm always optimistic. I'm going to push that we can get it out before Christmas this year, because that's when I think people get most excited about new books, is for the big end of year holidays.
Right, and then for folks listening, I'm sure for a good subset of them, like, you lit their curiosity on fire. How do they hear more about what you're talking about and interact with you, through your writings or in other ways?
Sure. I write the blog Starts With a Bang. It's hosted on Forbes. I also have a Patreon set up. You can find me on Twitter or Facebook. And for your listeners who are over there in Europe, you can check out this May Brain Bar over in Hungary, which is like Hungary's version of TED Talks, all in one 3-day extravaganza. This May, I'll be a special guest at Brain Bar, and I'll be speaking there about all sorts of mysteries of the universe. So if you want to get a hold of me, find me online, find me in real life, those are the ways to do it.
That's great.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.